Okay, so thank you very much once again. Well, maybe for the last talk, we'll be a little bit less explain things a little bit less, but I'll try to say a little bit more about the sort of the overall situation and what we know and what happens and so on. So this part is going to be, we would like to, one way of looking at what we're doing here is we'd like to do sort of an extension of Hodge theory. To non-abelian cohomology. Which is not the only possible thing, but basically, let's go back to X. X is what was S last time. H1 of X with coefficients and G but G is a non-abelian group. So this is going to be thought of as representations from pi 1 of X into G, modulo conjugation. So this is really a moduli stack. And the coarse moduli space is the representations modulo what's called S equivalence. Let's say G. SL. For example. And so the notion, so as we've seen, the Hodge theory is very closely related to them. I mean, the fundamental thing that you do in Hodge theory is you look at harmonic representatives for cohomology classes. Okay. So what plays the role of harmonic representatives? Plays the role of harmonic representatives for cohomology classes, or harmonic metrics. Let's say pluriharmonic metrics. And these correspond to solutions of Hitchens equations. So let's start with that. So as we were mentioning last time. So Hitchens equations. So we start with what you might call a Higgs pair, a Hitchin pair, or Higgs bundle. So what is that? So E is a homomorphic bundle. On X, and phi is a holomorphic map from E into E tensor omega 1x, and phi which phi equals 0. So what do you think? So an important way of thinking of phi, as we saw how it shows up last time, is it's like a connection, but it doesn't have the differentiation. So it's a connection operator, but with no differentiation. But formally speaking, it looks like a connection operator. So. Given an Hermitian metric on E, we can write d double prime equals del bar plus phi. So, I mean, this was not Hitchens' motivation for this operator, but as we saw last time, you can motivate this operator by Hodge theory. So this is exactly what we saw last time, but we don't suppose anything about a Hodge decomposition, okay? We just have a bundle and an operator. Then let's let del be the associated so del such that del plus del bar is the Hermitian, preserves the Hermitian metric. So there's a given the del bar operator, there's a unique del operator with the property that it preserves that connection. And then we have phi bar such that phi plus phi bar anti-preserves. And then we'll put capital D equal del plus phi plus del bar plus phi bar, the sum of these. And this is now a connection operator. Then its curvature as its curvature, I mean, it's just the operator d squared. D squared being an operator from 0 forms to 2 forms with coefficients. And Hitchin's equations just say that that's flat. And you can write those down in terms of equations for the curvature of this connection. I mean, a more usual expression of these equations has two terms involving the curvature of this connection, and then a term for the phi plus phi bar. On a curve, there's no kind of cross term, so the other term, there's the curvature of this guy plus, and then the commutator of these two. Now let's also look at the harmonic map equations. Sorry. The Flory harmonic map equations, they're kind of similar, but we start with a flat bundle. Sorry, I should say, these are equations for F, so we think of these as equations for H. Equations for this metric thing. And the solution is called the harmonic bundle. In the same way, we can start with the flat bundle, and then we choose a metric. And then we can write the flat connection as del plus del bar plus phi bar, such that del plus del bar preserves the metric, and phi plus phi bar anti-preserves the metric. Of course, I mean, there's a case, obviously, where you have a metric which is preserved by the connection. In that case, it's a flat unitary bundle, and the monodromy representation preserves the metric, so it's the monodromy representation is a representation into the unitary, okay, which is a compact group. So you might say this whole theory is kind of destined to treat the case where we have a non-compact group here. If you have a non-compact group here, then you can't have a metric which is fully preserved by D. So any flat connection has to have, and any metric has to have a piece which preserves the metric and a piece which anti-preserves the metric. But this decomposition into two pieces is kind of unique. I mean, sort of, if you take the connection views as a foliation, I mean, you can sort of project it onto the unitary direction and project it onto the anti-unitary direction. And then these are the decomposition into the Hodge type on X, both of them. Okay. Then we just say set d double prime to be del bar plus phi. And the harmonic map equations, the Plural harmonic map equations, are we can call this G. And if we can just do, this is just kind of analogous, we can just say, let's look at the square of this operator. And if this operator squares to 0, then that's equivalent, by looking at types, that's equivalent to del bar squared equals 0, del bar of phi equals 0, and phi wedge phi equals 0. So we get a Higgs bundle. Right? This says we have a holomorphic bundle. And this says that phi is a holomorphic map. So Donaldson and Corlett plus, let's say, it may be a Bachner identity. And generalizing yields in Simpson. They show that any semi-simple flat bundle over X, comma omega, which is compact Kähler, admits a pluriharmonic metric. And vice versa. If it has a pluriharmonic metric, then it's semi-simple. Okay. And then Hitchin for a curve shows that a Higgs bundle E comma phi admits a solution of the Hitchin equations if and only if E comma phi is polystable of slope 0. Then my sort of little contribution to this was in higher dimensions. This is generalizing Donaldson Batman Dow. Is that in higher dimensions, E comma phi admits a Hermitian Yang-Mills Higgs solution, which is to say lambda f equals 0. Instead of asking the curvature to be 0, we only ask lambda the curvature to equal 0. If and only if E comma phi is polystable at slope 0. And this is flat, which is to say f equals 0, if and only if the C2 means C1. so we get a correspondence of moduli spaces. So let's just write these down. The Betty moduli space, this is Hom from pi 1 into G. G is let's say SLR. I'm sorry, there's a certain number of terms here which are not defined and which we won't have time to define, like stable and stuff like that. So that's a different subject. So this is analytically isomorphic to what we might call the Durand moduli space, which is the moduli space of vector bundles with algebraic flat connection. So this is kind of an additional comment here, which is that these two moduli spaces, I mean, a priori they're the same in analytic geometry. In algebraic geometry, there's two different ways of looking at a flat bundle. We can think of it as a representation of the fundamental group, or we can also think of it as an algebraic vector bundle with an algebraic flat connection. And that's what shows up in the Gauss-Manin connection. Anyway, but the homeomorphism we get of moduli spaces is the Hitchin moduli space, which is Higgs bundles, like semi-stable. Modulo S equivalents. And we should have these Chern classes equal to 0. This is the Hitchin moduli space. So I mean, I'm hoping that, at least roughly speaking, it's clear what's going on here. We have these equations which go in both directions. So the Hitchin equations go in the direction from here over to here. And the harmonic map equations go from the direction flat bundle over to here. Okay. But if you have a solution of harmonic map equations, then you created a Higgs bundle. And by the same token, I guess you erased it. But if you have a solution of the Hitchin equations, then starting from Higgs bundle, you've created a flat bundle. So the solutions of those equations give you the maps going in the two directions. Then another theorem.
Last one is diffeomorphism.
Sorry?
Last one is diffeomorphism.
Well, no, it's a homeomorphism. I mean, it's going to be a diffeomorphism on the open subset, which is smooth. But these moduli spaces can be, and even at higher dimensions, they might even be non-reduced. I mean, but I mean, they will tend to be singular. I mean, even for curves. So for curves, if you take the moduli space of bundles, which are not flat bundles, but which are bundles of a certain degree and a certain rank, and the degree and the rank are co-prime, then you have a smooth moduli space, and you can say it's I mean, I think it's even real analytic. We know it's real analytic. A little more subtle point, which I don't think is still not really very well understood, is what happens at the singularity. So these moduli spaces have singularities when you have polystable but not stable bundles, which correspond to representations here which are not irreducible. If you have a representation here which is a direct sum of pieces, then the moduli space tends to be singular at that point. Let's say almost always. In that case, you can just say it's a homomorphism. And one would like to know a little bit more about the structure of those maps, but that's a difficult question. Okay, so that's kind of in a nutshell those. So now I wanted to point out, so the place of variation of Hodge structure. So the situation, I mean, let's say the location. What about the location of variation in the Hodge structure in here? So, so MH, this is the moduli space of things of the form E comma phi with some semi-stability condition. And mod some S equivalence. Okay. But roughly speaking, it's a moduli space for things of the form a vector bundle plus a phi. And so C star adds some. So if we have T in C star, it takes E comma phi. We just can scale the phi. And a little lemma is the fixed points fixed points of C star are bundles that decompose. So roughly speaking, if you have a fixed point of this, right, this is a moduli space up to isomorphism. So if you have a fixed point of the action on the moduli space, it doesn't mean that phi, it doesn't mean that t equals 1. It doesn't mean that phi equals t phi. It means that e comma phi is isomorphic to e comma t phi. So that isomorphism is an isomorphism of the bundle E. And if we look at the eigenvalues of that isomorphism and compare them with the values of T, the decomposition of E according to eigenvalues of that automorphism, that's going to give a decomposition of E into subspaces. And the phi behaves in a certain way, right? Because since this is phi and T phi, the phi thing has to go from the T from some tau eigenspace to the tau plus 1 eigenspace. So when we put that together, we can just say that we have E, and we can sort of make this look a lot more like Hodge theory by just adding a dummy extra index. So we can just choose K however we want. Okay. We're just kind of adding an extra index to make it look pretty. But the point is that if we add this extra index to make things look pretty, we can make it look exactly like what we had before. Okay, so the phi goes from E PQ into E P minus 1 Q plus 1. Okay, so this string of things here, this is a string, right? Because we're fixing P plus Q equals some fixed K. You can choose K however you want. So this is just really a one variable decomposition. This is the decomposition according to eigenspaces of that automorphism, okay? But then phi goes like that, and so this is going to actually correspond to a variation of Hodge structure. And the solutions of Hitchin's equation at those points equations give you exactly the equations of a variation of Hodge structure, but where you have to modify a little bit, you have to relax this condition of having a Q sub-vector space, because there's nothing in the solution of equations that's going to give you something rational for the mononomial representation. Or even relax the condition of having a real subspace, just have a complex subspace. So let me not give the definition, but you can maybe imagine the definition. Here, the main actor here is no longer the real structure, but it's the polarization form. So you have a flat Hermitian polarization form, but which is indefinite, and then it has this sign property. But so roughly speaking, for variation of structure. So the conclusion is that the fixed point set of the C star action is the set of C variation of Hodge structure. Then, of course, that's going to contain the Q variation of Hodge structure. So a corollary of this it says that if you have, suppose the moduli space is just a single point, okay? Or something, suppose the moduli space has a discrete point in it, then that point automatically has to be a fixed point, okay? So if you have a rigid representation, that's an isolated it's an isolated point in any one of these moduli spaces. So it has to be a fixed point set. So it has to be a C variation of Hodge structure. And a little bit of extra work. With a little bit of extra work, if you take a rigid representation and you add together its different conjugate representations, and work it to me a bit more, you can actually show that is in fact a complex, a C direct factor of a Q. So because, so let's just say a remark. If rho is rigid, then there exists a number field. Then there exists a number field K, such that rho goes from pi 1 into SLRK. Because if you have a rigid representation, it can't have transcendental parameters in the representation. Because if you have transcendental parameters, you can sort of move those parameters around and it wouldn't be rigid. So if you have a rigid representation, then it has to be defined over a field. Another way of saying that is if you have an isolated, if you have these algebraic, this algebraic variety MBETI, the MB thing, that's defined over like the integers or something. So if you have an isolated point, the isolated point has to have coordinates in a number field. So that's kind of I mean, you have to do a little bit more work here, but that's an introduction as to why this is true. Right? If you take this field, you take all the Galois conjugates of this, and you look at the Galois group with the Galois closure of this field, look at add together all the Galois conjugates of rho, and that sum will be a Q representation. Or another way of saying it is, I mean, if K has degree D over Q, then we can think of this as an element of SL, I guess, R times D of Q. That's the same thing. Okay, so this is the motivation for a conjecture. The conjecture is that a rigid representation actually has to be motivic. So let me just explain quickly what I mean by motivic. In other words, there exists a family of varieties Z over X. Okay, maybe not really necessarily smooth, like. Such that our representation of rho is a direct factor of the Gaussian function of Z over X. Right? I mean, that's what we've been doing. I mean, I've changed the letters. Z was X before, and X was S before, but I changed the letters. But remember, our whole lecture series, so we've been having a family of varieties, and then from the family of varieties, we get a variation of Hodge structure on the base. Okay. So we'll call those variation of Hodge structure, we'll call those motivic. Motivic because it means we're having a family of motives over X, basically. So we'll say that a representation of pi 1 of X is motivic if it comes from a family of varieties, so you have to make a few extra comments here to make it make sense. So we don't want to just necessarily look at the representation on X, but we want to look at the representation restricted to the pi 1 of a Zariski open subset of X. Because it's possible that the family of varieties that kind of represents this motive might not be smooth over all of X. But with more ecocytos theory of mixed Hodge modules and so on, that all makes perfectly good sense. And so we can prove this in a few very special cases. So.
For SO2 and then for SO3, some condition.
Thank you.
But that's what that are the special cases.
Those are the special cases, indeed. So one is if G equals SL2 bar. In this case, in my paper with the Corlett, we actually can in fact give a classification of all the representations. So maybe I should also probably comment. This is kind of called, this falls into what we call factorization theory. Of which Lou Mill was one of the main instigators. I mean, really, Hsu and Gromov were doing this before. But in terms of linear representation, the factorization theory of linear representation, well, that was work with Lou. And then the other case that we recently did with Longyear. And using a theorem that I know and Gorshany. It could show the conjecture for cohomologically rigid representations. Both of these are the cases of project. And so maybe let me just mention a corollary of that is that the tautological representation of any two-ball quotient B2 mod gamma is motivic. So these are things where in Mostel-Margoulis rigidity theory, we don't know that, I mean, there exist quotients of the two-ball where gamma is not an arithmetic group. And so what we can show is that in fact it still comes in some way from geometry, the representation from gamma into ESL. Comes from geometry in some way. So.
Let's see.
Okay, so so I'd like to next mention the next kind of main aspect of this whole picture. Which is the notion of spectral curve. Spectral variety, maybe. Spectral curve. So So let's just, for simplicity, let's suppose X is a curve now. This part of the theory doesn't really say, I mean, there's been some attempts, I mean, you can say something, but it doesn't say all that much. There was a paper by Ngo and somebody else recently about saying something about this, but I mean, it doesn't really work all that well in higher dimensions. I mean, you can say something, but this part of the theory mostly works better on, in the case of a curve, okay. So we have what's called the pitch and vibration. So we have the Hitch and moduli space of Higgs bundle. And we have a map to an affine space. And sometimes we'll call that B as the Hitch and base. So B is the direct sum, say I equals maybe 2 to R minus 1. So this is a vector space. Not sure it's R. Yeah. Okay. So this is a vector space, and this is a proper map. So in fact, it's a proper map. So the Hitch and vibration. Whose fibers are generically abelian varieties. So in other words, this presents this Hitch and moduli space as a fibration over a base, which is an affine space, and the fibers are abelian varieties, but maybe degenerate. I mean, there's singular fibers that can be degenerate abelian varieties, but the smooth fibers are abelian varieties. And so this is a completely integrable algebraically completely integrable system in the sense, Hamiltonian system maybe. The fact that the fibers are abelian varieties, I mean, in one point of view, that can be viewed as the property in this case that corresponds to saying that the invariant tori for a complete set of Hamiltonians for an integrable system is a tori. The invariant manifold for the Hamiltonians for an integrable system is a tori. So the functions on here, these are viewed as Hamiltonians. And this thing has an algebraic symplectic structure. Maybe I should just also mention before going off to something else. In fact, so M, H. In fact, it has a hyperkähler structure. That would go beyond our time left here, but the hyperkähler structure, we had this homeomorphism of spaces between the space of representations and the Hitch and moduli space. But that does not respect the complex structure. Those are two different complex structures. But those two different complex structures fit into a quaternionic triple. So those two different complex structures are two of the three complex structures of a quaternionic structure. So there's some kind of global structure which, and everything here was done in Hitch and paper. Hitch and paper like this has this gigantic amount of stuff in it. So that's a whole topic into itself. But so I just wanted to say here the first thing we should know about this whole situation is how to interpret this Hitch and vibration. So the Hitch and vibration may be viewed as the map which takes a point, which is a Higgs bundle, and maps it to what? It maps it to sigma over x, which is the spectral curve. Of phi. Viewed as a point inside of B. So these terms here in B, these are the different coefficients of the equations of the spectral curve sigma. What's the spectral curve sigma? So sigma is just a set of points x, comma, let's say, in the cotangent, it's a set of points in the cotangent bundle of x, such that u, right, such that u is in the cotangent fiber of x at the point x. So you just have to think about this for a minute, but it's not very difficult, which is that this phi thing is an endomorphism of the bundle, but twisted, so it has coefficients in the cotangent bundle of x. In our case of a curve, this is a line bundle. You can also call this kx. Okay. In the case of x as a curve, this is the cotangent bundle is a line bundle. So what is the eigenvalue of phi? Well, phi is an endomorphism of E, so it has eigenvalue. But since it's not really an endomorphism, it's an endomorphism but with values in this kx. It means that the eigenvalue is actually naturally an element of kx, not an element of C. Okay? Is that good, everybody? So it means that the eigenvalue, the eigen1 form of phi, is actually an element of the cotangent fiber T star x, x. And the spectral curve is just a set of all points x, comma, u, where u is one of these eigenvalues. Okay. A little bit more, a slightly more advanced way of saying this is that E, comma, phi corresponds to a coherent sheaf F on T star x supported on sigma, and E is just P or star of F. This is called the Mobilar-Simon-Ramona correspondence. Okay, so that's the spectral curve. And so if sigma is smooth, the set of f's supported over sigma is the set of line bundles on sigma. It's really in some kind of prim maybe. And this is an abelian pride. Why is it in a prim? It's in a prim because we're taking, I just kind of decided here to take the group to be SLR, not GR. If you take the group to be GR, then it's really just the Jacobian of the spectral curve. If you take the group SLR, you should divide by the line bundles coming from X. So it's the prim variety. This kind of should explain, roughly speaking, why. In the case of a general sigma, so that the rank of sigma, the degree of the map from sigma to X is actually R, same as the rank of the bundle, then the F is just a line bundle over sigma. And the family of those line bundles, that's this abelian variety. So maybe let me just finish. So what I wanted to, the other thing I wanted to say, we haven't completely finished what I wanted to say, but almost. I'm sorry, I skipped over quite rapidly, some parts of it, obviously. So let me apologize for that. But let me, so the last thing I wanted to say, which we can relate a little bit to this, as we'll see in a minute, which is Dolbeau cohomology. With coefficients in E comma phi. So the question here is, rather simple. It's, suppose E comma phi, the Higgs bundle, suppose it corresponds to V comma D, a flat bundle. Or, a representation. Well, then we have we can look at H, K of X with coefficients in V comma D. And we can look at the Durand cohomology of X with coefficients in this flat bundle, which is the same thing as the sheaf cohomology of X with coefficients in the sheaf of flat sections of the bundle. So the question is there, so given how natural this correspondence looks, there should be some way of describing this answer in terms of the Higgs bundle. And, well, in fact, Zucker's theorem tells us how to do this, basically. And so Zucker's theorem tells us how to do this for the case of variation of Hodge structure. In other words, add a C star fixed point. So in fact, in the previous lecture, we already saw exactly how to do this, because we saw that the cohomology of X with coefficients in the variation of Hodge structure is represented by harmonic forms, but then the harmonic forms, the D harmonic forms, are equal to the D double prime harmonic forms. And at the end of last time, we saw that the D double prime harmonic forms are given in terms of the cohomology of a complex that we can write down using E comma phi. Okay. And so it turns out that the exact same thing works, and that's kind of the miracle of the Hitchin equations here, is that you don't need, the stuff which would be true using the Hodge decomposition, you actually don't need the Hodge decomposition for it to be true. So that's kind of, and so that remains true here. So the answer, it's just write down the same Dolbeau complex as Zucker does, but without the Hodge decomposition of E. Okay. So and we can just write down what this is. This is just easy. We just write down, there's really only one possible thing you could do here, you might say. If you go home and sit down and write out what could I possibly do here, you'll come up immediately with the answer. There's only one possible thing you could do here, which is to write down a complex where we take E and we put phi in the complex. And this condition phi wedge phi equals 0 implies that it's a differential. Okay. So on higher dimensional variety, the condition phi wedge phi equals 0, which is kind of necessary to get a flat bundle and so on. That plays a role here, and so it just tells you that you get a complex. So this is actually a complex of, these are not differential operators anymore, these are just functions, so this is a complex of homomorphic vector bundles. And one can do the Dolbeau resolution if you want. Our answer is that H K of X comma V D is equal to the K hypercohomology of this complex. So this is the only kind of tricky thing we need to do here, which is that this is a complex in the holomorphic category, these are not acyclic things. So when you do the cohomology, you have to take the hypercohomology. One way of calculating the hypercohomology, let me not write this down, but one way of calculating the hypercohomology is to make the Dolbeau resolution, which was the same one we wrote down on the board before.
Yeah, but Carlos, in terms of shifts on T star X, just are home from the structure shift of the zero section to E. To F.
That's true. That will be related to what I wanted to say. In fact, yeah, a few minutes to say that. So Sasha points out correctly that this is some kind of thing which is concentrated on the zero section of P star X. Okay, but anyway, we just take the hypercohomology of this complex. One way of computing that, if you like, is to do a low resolution vertically in each bundle with a d-bar operator, and then make a double complex. And that's going to be exactly the same double complex that I wrote down before, but just without the extra Hodge types. But as I was saying before, when I wrote that down, I just stopped writing down the Hodge type anyway, so it was really writing down the same thing. Then you take the global sections of this big complex here. But that might not necessarily be the best way of calculating it, as we'll see in a minute. But anyway, so this is, or otherwise you have to go find a book and read about, or look up Wikipedia hypercohomology or something, and figure out what that means. Anyway, it's the cave hypercohomology of this complex. Let's just call it E tensor omega dot. With phi. So let's just do an example here. So I'm sorry that I haven't been able to do more examples. I had some examples I wanted to say, but let's just do an example. Suppose E has rank 1. So suppose E is a line bundle. I guess it's not going to be an SLR, it's going to be a GL1 example. So if we take, in this example, if we take E, if we suppose E is a line bundle, that's going to correspond to rank 1 representation. So I mean the representation row is going to be mapped from pi 1 of X into C star. But this can exist if X has a non-trivial abelianization of the fundamental group. So like typically it's going to be a subvariety if it's an Albanese variety, then it's going to exist. So E is a line bundle. Well, the endomorphisms bundle of a line bundle is just always OX. It doesn't depend on E. So in this case, it's sort of a decoupled version of the equation. And then phi is just in H0 of X omega 1X. And phi which phi equals 0 is automatic. And then this Debye complex let's write it all the way up to the top. If the zeros of phi are isolated, then if we define this, if we take the co-kernel complex, we call this Q, the co-kernel sheaf. If the zeros of phi are isolated, so we have a differential form where zero is isolated, then in fact so this can happen, right? Because phi is a section of a rank n. I mean, if X has dimension n, then phi is a section of a vector bundle of rank n, right? So being vanishing is locally n equations. So having phi vanish is locally n equations in n variables. So I mean, a general case in some way is the case where the phi has isolated zeros. Okay. So this can happen. Okay. Then the sheaf Q has finite support, and this complex is its Koszul resolution. This is kind of a version of what Sasha just said in an example. Okay. And so it follows that the hypercohomology H dot of this complex is just isomorphic to the hypercohomology of the complex Q placed in, so is this a plus or a minus? Sasha, maybe you know. So I put a minus or a minus n or a plus n or something. Anyway, this means the complex where Q is placed in degree n, okay? Somebody?
It's minus.
Minus, okay. Okay, the complex with the sheaf Q, that's just the coherent sheaf, which is, but this is just a finite, this is a sheaf with finite support, right? So this is just a zero-dimensional sheaf placed in degree minus n, right? So this has to be 0 if dot is different from n, and it's equal to h0 of q if dot equals n. Okay. So in this case, this is kind of interesting. So this really, you actually can get a nice calculation, which is different from a calculation you would get from the Durham picture. I mean, you wouldn't see this calculation in the Durham picture in some way. And this is related to Green-Lazarfeld theory. And I think that, I'm not sure, I'm not sure if it's safe to say this, but I think it's somewhat related to this stuff that Kontsevich does about exponential motives and stuff like that, possibly. Anyway, but so you can see that here you get a really nice kind of answer in this case. So that's kind of the last thing I'll say. So let me just flesh out a teeny bit what Sasha was saying in general. So more generally, you might say the same type of considerations, so similar considerations. So that if we take sigma inside G star x, the spectral variety of E comma phi, then this hypercohomology of E tensor omega dot x is somehow they're concentrated along the intersection, sigma intersects the zero section. Let me just put it that way. Okay, let's see here. Covered everything except for the example. Okay, maybe just a small, just have 2 minutes left. Just in my list of things I wanted to talk about, so this is not really a sequence from here, but I just wanted to say, like the first basic example. Well, no, let's do it in the middle order. The first basic example is the uniformizing Higgs bundle. That's an important example to understand, in fact. So maybe it's a good way to finish here. So the first basic example of the Higgs bundle. So X is a curve. Genus G greater than or equal to 2. So let's take E. So we'd like to write down the Higgs bundle. And in fact, it's going to be a variation of Hodge structure, so it's going to be one of these things we've been talking about. And we're going to take k to the 1/2, kx to the 1/2, plus kx to the minus 1/2. And phi is going to go from kx, from here to here. So this is the Higgs bundle fixed by C star. And so it corresponds to a complex variation of Hodge structure. It depends on a choice of theta characteristic, right? It depends on a choice of k to the 1/2. Okay? So there's 2 to the 2g of them, I guess, something like that. it corresponds to a variation of Hodge structure, so I guess I should apologize here. I wanted to talk about the period mapping of the variation of Hodge structure, but didn't get time, but the period mapping. I mean, in this case, what does the period mapping really mean? It really just means there's this there's this subspace, which is the Hodge filtration, right? We have a rank 2 bundle, and we have the Hodge. There's only 2 Hodge subspaces, each of which has rank 1. There's only one level of the filtration. That filtration, that's a line inside a rank 2 vector space. Okay. So we get a map from. So if we use the monodromy operation to transport everything back to the base point, we get a sort of a varying family of one-dimensional subspaces. And those one-dimensional subspaces have to be positive definite for the indefinite scalar product. When you put all those together, you get a map from the universal cover of X into let's say, should I say, well, yeah, so, so this is like the most basic Higgs bundle you can write down, which is just a direct sum of 2 line bundles, and the phi is just an isomorphism like that. That actually corresponds to the uniformization of X, right? The constant negative curvature metric of X. So maybe I'll stop there. So that's like the first example to look at. Anyway, so let me just say thank you very much to the organizers, to Lumil and Peter and all the organizers for organizing this nice event. So it's a great pleasure and a great honor to have been able to speak here. And also to visit Sofia for my first time, which I'll be back for. So thank you very much.
Questions?
So, what of what you did say here doesn't go in for higher dimensional special coloring?
Well, the fact that this is a vibration. I mean, the map from. I mean, it's hard to say what the target of the Hitchin vibration is going to be, and it's not going to be a vibration in general. I mean, most of the fibers are empty. I mean, if you try to write down some equations for the spectral variety. So Ngo had a paper recently where he did that maybe a little bit better, but I still don't know what exactly. You can't say too much in higher dimensions. For a curve, I mean, the map from the Hitchin moduli base to this base is surjective map and has fibers which are abelian varieties. That's not going to be true in higher dimensions. I mean, the image of that map might be some strange thing.
Still, you have an absolute algebraically completely integrable system over the image of the map.
Well, but it's not clear that the fibers will be smooth. I mean, look, the most common case in higher dimensions is the case of a rigid local system where everything is on the 0 fiber. And I mean, I have to say I don't really know what the general picture is. I mean, I don't know what the general picture would look like in higher dimensions.
And so in the exponential cost structures, you usually have some potential. What plays the potential in what you are suggesting here?
Well, I think it's just that it's just that phi is equal to df, dw of the potential essentially.
Of course, we couldn't get to any higher cohomology on a different cohomology.
Yeah. But this is the first cohomology is kind of the main thing. So at least so far.
So I think we should thank Carlos for this a task.
So, once again, thank you, Carlos. I'm sure we'll see you again. So, a couple of announcements. So, don't forget, of course, there are office hours, but before you leave, don't forget to make some comments on the website of the center. Leave us some recommendations, comments, suggestions, criticism. So, we're just starting, and these things are really important for the future of this center, to make this better for you. And indeed, so we have prepared wonderful events coming later in June and July. So in June we have a course on directional geometry, and the lecturers will be Yuri Chinkel from Science Foundation, Ivan Shortsov from Edinburgh, and Yu Fan from Berkeley. So I hope to see at least some of you at this event. And then there's a big inaugural conference in July, starting July 15. You can find all the information about this on the website of the center. Once again, thanks a lot, and don't forget to give us your feedback. Carlos, thanks again.
Okay, thank you.